ঠিক আছে, আমরা এটা ইন্টারঅ্যাক্টিভই রাখবো যতটা সম্ভব, ঠিক আছে, তাহলে ব্যাপারটা আর কি ভালো হবে। আচ্ছা, তো আমরা বেসিক্যালি একটা এই পার্টিকুলার রিডিং প্রজেক্টটাতে একটা বই করতে চাই, সেটা হচ্ছে ট্রিজ, বইটার নাম হচ্ছে ট্রিজ, এবং আমি বইটার পিডিএফটা তাদের দিয়ে দেবো। এটা বাই স্যার। জিওমেট্রিক গ্রুপ থিওরির ওপর যদি আমি ওটা নিয়ে কাজ করি, জিওমেট্রিক গ্রুপ থিওরি নিয়েই কাজ করি, কাজে আমাদের প্রজেক্টটা জিওমেট্রিক গ্রুপ থিওরির ওপর হবে। ট্রিজ যে বইটা আছে, এইটা আমাদের একটা ফাউন্ডেশনাল ওয়ার্ক হিসেবে ব্যবহৃত হবে, এবং এর ওপর দাঁড়িয়ে তারপরে আমরা অন্যান্য রিডিং মেটেরিয়াল তখন অ্যাক্সেস করতে পারবো আর কি। ঠিক আছে, আমার কথা শুনতে পাচ্ছিস? হ্যালো?
আচ্ছা
আচ্ছা আচ্ছা। তো এখানে যেটা স্টার্টিং পয়েন্ট, যে বইটার যেটা স্টার্টিং পয়েন্ট, সেটা হচ্ছে ডিরেক্ট লিমিট আর ইনভার্স লিমিট দিয়ে। তো ডিরেক্ট লিমিট আর ইনভার্স লিমিট কি তোরা দেখেছিস আগে? না হলে আমরা এটা একটু আলোচনা করে দেব। ডিরেক্ট লিমিট, ইনভার্স লিমিট, এই দুটো কনসেপ্ট কি তোরা আগে দেখেছিস? রাজস্বী আর সৌম্যদীপকে বলছি। হ্যালো?
না স্যার, আমি অতটা ভালো করে জানি না কনসেপ্টটা।
আচ্ছা আচ্ছা, ঠিক আছে, এটা আমরা একটু দেখি। এটা খুব ইম্পর্টেন্ট অ্যাকচুয়ালি, কারণ এটা ব্যবহার করে ম্যাথামেটিক্সের অনেক কিছু আমরা করতে পারি। তো ডিরেক্ট লিমিট নিয়ে কথা বলবো। তো সিকোয়েন্স অফ তোরা গ্রুপ মেনটেন করতে পারিস। জিআই বলে একটা সিকোয়েন্স ফ্যামিলি অফ গ্রুপস আছে, যেটা ফ্যামিলি অফ গ্রুপস। আর আইজে, এফ আইজে হচ্ছে একটা সেট অফ হোমোমরফিজমস। তার মানে জি আই থেকে জি জে অবধি একটা কালেকশন অফ হোমোমরফিজমস, সেট অফ হোমোমরফিজমস। বাই দ্য ওয়ে, গ্রুপ কাকে বলে, হোমোমরফিজম কাকে বলে, এটা এগুলো এগুলো কি জানিস রাজস্বী আর সময়? একটু ইন্টারাক্ট কর, তাহলে বুঝতে পারবো আমি।
স্যার এগুলো
এটা জানিস?
হ্যাঁ জানি এগুলো স্যার।
সেটটা আছে, এটা বেসিক্যালি set of homomorphisms. Yes, Pranav, I can see the comments. Set of homomorphisms from GI to GJ. F12 G2 থেকে G3 যাচ্ছে F13 এরকম আর কি। কিন্তু এই F12 F23 F13 এগুলো কোনো একটা ম্যাপ নয়, অনেকগুলো ম্যাপ আছে। হয়তো 2 আছে, G12 আছে, H12 আছে, অনেকগুলো ম্যাপ। For Serre, it's a set of homomorphisms from G1 to G2. ঠিক আছে? Data. Now, using this given data, we want to create another group. So our group, a group G, which we will write as lim GI, which is basically the direct limit, of this collection of groups. আর আমরা কি করতে চাই? Create a set of homomorphisms Fi from GI to G. ঠিক আছে? Such that F is equals to Fi for all F in Fij. শুধু তাই নয়, আমরা এই যে গ্রুপটা আর এই যে কালেকশন অফ হোমোমরফিজমস, এই ইউনিভার্সাল কথাটার মানে আমরা বুঝে নেব। কিন্তু তার আগে দেখ, আমরা এই ডায়াগ্রামটা দেখলে সব ব্যাপারটা পরিষ্কার হয়ে যাবে। ব্যাপারটা হচ্ছে যে G1 থেকে G2 অবধি এই ম্যাপ সেট অফ ম্যাপস আছে F1, F12, ঠিক আছে? এই F12 হচ্ছে a collection of homomorphisms from G1 to G2. F12, G12, H12, এরকম অনেকগুলো ম্যাপস আছে আর কি, মেবি একাধিক ম্যাপস থাকতে পারে আর কি F12 আন্ডারে। তো আমি একটা এরকম such that G1 থেকে ক্যাপিটাল G অবধি স্মল F1 বলে একটা ম্যাপ থাকবে, G2 থেকে ক্যাপিটাল G অবধি স্মল F2 বলে একটা ম্যাপ থাকবে। যে তুই এখান থেকে যে কোনো একটা ম্যাপ নিয়ে নে, এই কালেকশনটা থেকে যে কোনো একটা ম্যাপে তুই যা পাবি, তুই এরকম এলেও তাই F12 ব্যবহার করিস, মাধ্যমে এখানে গেল। তারপরে যদি তুই F ব্যবহার করিস, সেটা হচ্ছে F1. This is the meaning of the sentence that the diagram commutes. This is the meaning of the sentence the diagram commutes. তার মানে তুই এরকম ভাবে গেলে যা হবে, তুই সরাসরি এলে তাই হবে। পিকচারটা যদি আরেকটু ভালোভাবে ড্র করি হয়তো আরো পরিষ্কার হবে। আমি আরেকবার ড্র করছি। তো ব্যাপারটা এরকম যে যদি আমার কাছে একটা গ্রুপ থাকে G1, যাতে G11, G12, G13 এরকম অনেকগুলো এলিমেন্ট আছে। আরেকটা গ্রুপ আছে G2, যেখানে এলিমেন্টস গুলো আছে G21, G22, G23 এরকম অনেকগুলো এলিমেন্টস আছে। আর আমি যে গ্রুপটা বানাতে চাইছি অর্থাৎ ক্যাপিটাল জি, এটা আমি বানাতে চাইছি। হ্যাঁ, so this is something I want to create. This is what I want to create. So there are these points. Maybe I can say just G1, G2, G3, G4 এরকম, maybe these elements are here. Okay, so what is it that I want to create? I want to create G. My goal is to create this group G, and my second goal is to create these maps. যে ম্যাপগুলোকে আমি বলছি F1, F2 এই maps. So create the maps F1, F2, F3, etc. So F1 is from G1 to G. F2 is from G2 to G. F3 is from G3 to G, and so on. So just a second. Okay, so this is what I want to create. So what do I mean by the diagram commutes? In an ideal world, suppose G11, so this map is suppose cap small f12. So f12 of G11, that is something here, right? Maybe that is G22, maybe this is G22, maybe this is G22, maybe this point goes here, G22. Maybe F12 maps G11 to G22. Then F2 maps G22 to, maybe it maps to G3. So if I compose with F2, now this becomes G3. What it means is that if I apply F1 on G11, it directly goes to G3. So these maps are compatible. এবার বোঝা যাচ্ছে কি মানে কম্প্যাটিবিলিটি অফ দ্য ম্যাপস কথাটার মানেটা কি? রাজস্বী, সৌম্যদীপ, এটা কি বুঝতে পারছিস কি বলছি আমি?
Yes, sir.
আচ্ছা,
Yes, sir.
so this is the meaning of the word that the maps are compatible. Acha, now we understand the goals, but now we have to also understand the meaning of the word universal. এবার আমরা এটা বুঝে নেব। তো আমরা প্রথমে এটা খুব ইন্টারেস্টিং মেথড অফ ওয়ার্কিং উইথ দিস টাইপ অফ থিংস। You first decide what you want and then you create it. So the thing is, you first decide what you want and then you create. Okay, so আমরা বলছি যে আমাদের কাছে যদি এরকম একটা সিকোয়েন্স অফ গ্রুপস থাকে তাহলে আমরা এই জিনিসটা বানাতে চাই। এবার আমরা দেখবো যে জিনিসটা কি করে বানাতে হয় আর কি। So first let's understand what else we want. We want the universal property. তো ইউনিভার্সাল প্রপার্টিটা কি? বুঝতে গেলে আমাদের পিকচারটা আরেকবার বুঝতে হবে যে আমাদের পিকচারটা কিরকম ছিল। G1, G2, G3, G4 এরকম কালেকশন অফ গ্রুপস ছিল। কালেক্ট F3, 4. This is a set of homomorphisms. এটা কিন্তু একটা homomorphism নয়. Apps like this. I'm not drawing those because it will make the picture more. And we have asked for a group and a collection of maps like this. A collection of maps are F1, F2, such that so I explain what commute means. Now, this is universal in the sense another group H1, P, H is a group, a family. So the diagram will commute here as well. If that there is exactly one homomorphism, there exists exactly one homomorphism, small h from G to H. Hi is equal to H composed with Fi. That the most important part to understand is particularly factored. H1 can be H2 can be factored as F2H. H3 can be factored F3H. So if you know small h, which is there, which exists uniquely by the universal property, at least that's what you want, then Hi, each of these maps composed with Fi. H composed with Fi. So this is the meaning of universal property. This is the meaning of universal property. Say that then if this happens, then G is said Gi relative to Fij. Okay, so this is what we want. This is what we want. And if this happens, then G is say of these collection of subgroups Gi, whether there is such a group. So here is the question. Does G does G very weird thing to say, because we took such so much time to actually define. We don't even know whether or not. We don't even know that whether there is such a thing called G. We want this to exist, of course. Otherwise, why would we take so much time to prove to define it? So indeed, the proposition one that Serre proves is the pair consisting of G and the family Fi, where I is in I, exists and is unique up to isomorphism, up to unique isomorphism. So this is the first proposition, and we are going to show that this is indeed true, that it there is such a thing as G. There is a sense that you can now, and I'll show you exactly how he does that. But first, I will, since this is a lot of information, lot of data, we have given data, we have the given data G1, G2, G3, and so on, and a collection of homomorphisms, and there is, of course, F1. And so we have this collection of groups and collection of homomorphisms. Collection of homomorphisms. Okay. So these are the two things that we have. We want what we want. We want to make a group G and another set of homomorphisms. So F1, F2, F3, etc. So we want to make a group G and another set of homomorphisms, set of homomorphisms Fi from Gi to G. See how I have created the arrows, right? F1 is from G1 to G, F2, such that if you first perform so let me write that more clearly. J, which basically means small f is a homomorphism from Gj in that collection. Then if you first perform small f and then perform fj, so first perform small f, then perform fj, you are going to get arrows commute. In that sense, these particular arrows commute to make another set of homomorphisms such that G and the collection Fi is universal. What does that mean? That means if there is another group H with these set of homomorphisms H1, H2, H3, H4, and so on, such that these also commute, then there is a unique homomorphism from G to H. We call it we call it small h, such that H1 will factor as H times H composed with F1. H2 will factor as H composed with F2, and so on. So that's the meaning of universal. We want to show that such a group exists, such a group, and so we want to show that these things exist and they're unique. Okay, so how do we show existence? So let's do that. Let's show existence. And okay. Are you following up to now, Shomod, Shomadeep and Ravishi?
Yes, sir.
Okay. Okay. So let's see. Um, let's see. Okay. So we have this. Now let's see what we can do with this one. You see, how do we show that it exists? So first, we have to think about first. Let's think about how to create G. How do we define a group? How to define a group? So one way to do it is that we can define a group define a group by giving you the generators and the relators of that group, right? So, since you know groups, you must be aware that a group has certain elements which can be regarded as generators and certain relations among them which are called relators. Of a group, this is basic
Yes, sir.
group theory. Okay. So what we are going to do is we are going to
Yes, sir.
define the generators and the relators. Okay. The following generators of G as S1 square, disjoint union S2, disjoint union S3, and so on. So S1 is the generating set of G1. S2 is the generating set of G2. S3 is the generating set of G3, and so on. So take the disjoint union of the generating sets of each of the GIs. And there that is how we define the generating set for capital G. Now let's define the relators. So now we will talk about the relators. So the relators will be like this. We will take XYZ inverse if XYZ belongs to some GI and Z is equal to XY in GI. So basically take all the relators of GI. Okay. And we will also take XY inverse where X is in GI, Y is in GJ, and Y is equals to Fx for at least one F in Fij. Okay, so I will I'll tell you what is happening here. If you draw pictures, this will be extremely simple to understand. It's probably a little bit more confusing when you are looking at it like this. So if you look at G1 and look at G2 and look at G3 and G4, so you have these elements here. Let me draw them in different colors so that I can describe them in more efficient way. So suppose this one is mapped here, this one is mapped here, and so on. Okay. So inside the big group G, we will describe all of these elements as equivalent elements. Why? Because they are connected by these maps. So if this is X and this is Y, then there is some f in f12 such that fx is equals to y. So there is some map in this collection of homomorphisms that takes this dot to this particular, these two as equal inside this big group G. Okay, there's something very beautiful is happening here. Notice that we have taken all the members of G1 and G2 and G3 and G4, all of them are inside G in some sense. Do you see that? If you take the generating set of G1, if you take the generating set of G1 and the generating set of G2 and you have enough stuff to create all the things in G1, all the things in G2, all the things in G3 and so on. How we will declare things to be equivalent? Well, we will declare whatever relations are inside G1. Okay, we will insert them in the related set of capital G. That is true. Additionally, if x is mapped to y, we will declare x is equal to y. That we couldn't have done in the context of G1 or G2 because y is not in G1, right? You cannot declare x is equal to y inside G1 because, of course, y is not in G1. So you cannot do that. But when now you are allowed to declare elements from different groups to be equivalent using this maps or homomorphisms as bridges. So since x is mapped to y, you declare x is equal, then you will declare y is equal to z. Or in other words, xy inverse is identity, yz inverse is identity, and so on. These roads that we are creating, maybe these, and you are right, you will be right, but you have to be a little bit careful because it might so happen that will be the same road after a while. So it might so happen that these two roads are meeting at a certain point, and from that point onward, they are the same road. But essentially, this is what's happening. The the Fij's the Fij's acting as bridges that two points in two different groups equivalent. It's very beautiful. You are using these maps to glue points. X is from G1, there is no way to actually to glue x with y. How do you do that? Well, you take a map f from f1 to equal to fx. Let's declare x to be equivalent with y. Actually what's going on here. In the direct limit, when you are creating this group G, you are actually using these homomorphisms homomorphisms from G1 to G2, G2 to G3 to declare points which are equal. Now have the set of generators, which is the disjoint union of the set of generators of all of these constituent groups, and the relators are obviously the relators of each of the GIs, and the relators that are coming from the If x is equal to y, then you just use that to define that homomorphism. Okay, so I do you understand, Shomodeep? Is this making sense?
Yes, sir.
Okay. Okay, so I'm assuming that this is making, this will be very up. We will limit, which is the amalgam. One is a very simple. The given data is exactly three groups A, G1, G2, and two homomorphisms. So A to G1, which is F1, and A to G2, which is F2.
Not coming at times, sir.
Can you hear me?
Getting.
Just a second. Maybe I.
It's okay, I guess. Hello.
Yes,
Sir. Now it's clear.
now it's clear. Have so that's the reason. There is some. It's clear now.
Now it's clear.
Okay.
Sir. Yeah.
Okay, that's fine. Just a second. I'll just get one moment. Okay. I will just get some extra data for this particular session. UPI. Okay, yeah, this is working now. Fine. Okay, so before we go to the example, let me just do one thing. let me just show you that indeed the group that we created works with the definition. Okay, so we have this G1 to G2 to G3 to G4, right? And we just created a group G whose description is this: S1, S2, S3, etc. And XYZ inverse if some GI if XYZ belongs to some GI and XY is equal to Z in that GI, verse if R, so this is the stuff that we got from the maps. So if FR is W F in Fij, such that R belongs to GI and W belongs to GJ. So we have now okay. These maps G1, G2, G3, G4, etc. How are we going to define the maps G1, G2, G3? Notice that if if GI, if G1 is in G1, or maybe I can just, if G belongs to G1, then since the generating set, I will, maybe I'll just assign this, the final part of it, as a homework. Okay, so do you understand when I say that F1G is the equivalence class G? Do you understand what I mean by that? Basically, if G maps to H maps to W maps to R, so on, then the equivalence class of G is basically this particular set. G, H, those things. I guess, can you still hear me? Hello?
Yes, sir.
Yes, sir. Now, okay.
Yes, sir. It's okay now.
Yeah, so the so everything which is maps how this so can you check that this particular construction works and all the maps f1 f2 f3 these are well defined?